Başlayabiliriz.
Herkese merhaba. Hocam özür dilerim. Herkese merhaba. Öncelikle hepiniz hoş geldiniz. Bu oturumumuzda Gebze Teknik Üniversitesi'nden doktor öğretim görevlisi Roghayeh hocamız bizimle birlikte. Hocam hoş geldiniz. Aramızda olduğunuz için çok mutluyuz.
Teşekkür ederim.
Hocamız bugün Cut Vertices and Character Graph başlıklı konuşması için ben hiç sözü uzatmadan sözü size bırakıyorum. Sizdeyiz hocam.
Teşekkürler. Okay, I will start with English. In English, first of all, I would like to thank you for the invitation. And okay, I prepared some notes. I hope that it will be useful. And I'll start if there's no problem. Okay, let me start this. So I think you have my screen. Yes. Okay, this is part of a joint work with Muhammad Ali Hossein-Zadeh and Samana Musayizadeh and Ali Ramanish. These are my colleagues from Iran that we actually work on some projects. So sketch of my talk is, first of all, I will start with some basic definitions and results. You may be familiar with or not, some topics on character graph and of a finite group, and then our main result with actually with respect to the results in this paper. Okay, so some basic definitions and results. What do I mean by group action? Probably most of you are familiar with these notations. Notions actually, the group action, I have a non-empty set like X, a finite group like G, and I defined a function from the Cartesian product of G and X to X. It's an any pair like G and X to G dot X, which is an element of X. With these two properties that I mentioned by property 1 and property 2. So the action of the identity of G on any element of the set gives you the element itself. So it fixes this element. And when you consider two elements of a group like G1 and G2, so you have, according to the group operation, you have G1, G2, and then this is an element of group which acts on the element or the point X. So you should have this property, this equality. If you have a property 1 and 2 together with this function, then you said, okay, the group G acts on a set X via this action. So in particular, in my talk, I'm going to work with linear actions. What do I mean by a linear action? So by a linear action, I mean an action of a group and a vector space which preserves the properties of vector space. I mean, which preserves the vector addition and scalar multiplication. So what do I have as a set here? A set is a vector space over a field F. In my work, F by F, I mean the field of complex numbers. So even if I don't mention this, F is the field of complex numbers. So we have a vector space over a field of complex numbers. And here, whatever I mean by a vector space, always I mean finite dimensional vector spaces. So finite dimensional vector spaces. And G is a finite group. So a group here is always a finite group. I say that G acts on V, so normal action, whatever we discuss here. And we have the following two properties. So more than the properties that we have for action, for one arbitrary action, we have these two properties, 1 and 2. This gives me the linear action of G on a vector space V. So as you can see, we have the vector addition alpha plus beta. So G preserves the vector addition. And we have scalar multiplication of C and alpha. So G preserves, I mean, this action preserves the scalar multiplication and vector addition. Because of this, we call it as a linear action. So as an example, suppose we have a vector space. Again, remember this. Okay, here can be any field, of course, but in my talk, you can consider it always as the field of complex numbers. Now, as a group, I consider the group Z2, the cyclic group of order 2. You know that 0 is the identity of this group and 1 is the generator. So you can see that Z2X and V is any vector space over this field. So you can see that you can define an action of Z2 and V in this way. So the identity, according to the properties that we have for group action, identity send alpha to alpha itself for any alpha. And the other element of the group was 1. I define the action of 1 on alpha to be minus alpha, which is obviously one vector in V. Yeah. So you can easily check that this is a linear action. You can check it for yourself. Now, with respect to this action, I can obtain a homomorphism. How? I define phi from G to GLV. It's an any G to actually a linear. Remember, a GLV is the set of all invertible linear let's say, what is it, operators on V, on vector space V. So this phi index G is just a linear operator of V. And how does it behave? It behaves with respect to the action of G on V. So it's an any alpha to G dot alpha, which is the action of G on alpha. Then for yourself, for those students who have passed, let's say, algebra 1 and linear algebra also, you can check that, okay, this phi index G is one element of GLV, and phi is a group homomorphism. You can easily check these two properties. In particular, we have this property that, okay, we have the identity element phi. Remember, our G here was the cyclic group generated by 2. So the identity element was 0. Yeah. So if you are familiar with group homomorphism, we know that the phi, which is a group homomorphism, send the identity of the first group to the identity of the second one. So phi index 0, which is actually, with our notation, this is phi of identity of G. Yes. So this must be identity of GL of V, which is ID, the identity linear transformation on V. And phi index 1, which was exactly phi of 1, yes, 1 bar or 1, which was the generator of Z2, actually is exactly minus alpha because of this way of defining phi index G. So this was just one example of a linear action of a group on a vector space. And we obtain, actually out of this linear action, we obtain a homomorphism. Now, we can generalize this. We can see that given any linear action of a group on a vector space V, given any group G and a vector space V, then there is a one-to-one correspondence between the set of all linear actions of G on V and the set of all homomorphisms from G to GLV. It means what? It means given any linear action, you can write one homomorphism from G to GLV, similar to the thing that we actually did it for the previous example, and vice versa. Starting from a linear, from a homomorphism of G to GLV, you can write a linear action of G on V. Any element of this set N, I denoted by this N, it means any homomorphism from G to GLV is called a representation of G. So any element of N is called a representation of G. If you are not familiar with representation of a group, then actually this is the best or the easiest way to explain representation of a group. So this is, you can consider it as a homomorphism from G to GL of V. What is V? V is a vector space. And this homomorphism actually gives you one linear action because of this correspondence of G on V. Okay. So from now on, when I mention a representation, you know, I may mention it as a homomorphism from G to GL of one vector space, or I may mention it with, okay, I may start with one linear action, and then I say, okay, the homomorphism with respect to this linear action is the representation that I want. So suppose we have a representation X from G to GLV with respect to the linear action of G on V. Suppose, as I said, we are working with finite dimensional vector spaces. So suppose dimension of V as a vector space over C is n, and consider G in G, okay, G one element of G, and choose one basis for your vector space, an ordered basis. So again, those who are familiar with the topics in linear algebra, they can follow that. I can consider, remember this was one matrix in GLV. So I can consider the representing matrix of this linear transformation, this linear operator, with respect to a basis of this vector space. So I fix this, I choose it arbitrary, and I fix it. I consider the representing matrix of this linear operator with respect to beta. Of course, this is a matrix, and by a matrix, whose entrices actually they are inside the field of complex numbers. So I obtain a matrix out of this representation. I can define a function which is denoted by this notation chi from G to C, such that I send any G to trace of the matrix, the representing matrix of X index G with respect to beta. So you may ask, okay, you choose one basis. You started working with one basis of a vector space. What will happen if I change this basis? If I obtain different values, then it means that this chi is not well defined. But this is a topic in linear algebra that we know similar matrices have the same traces, yes. So whenever you change the basis, for example, if you, instead of beta, you work with beta prime, so this gives you one matrix of this form, and this gives you one matrix of this form. But this is a topic that in linear algebra that matrices of change of, when you change the basis, these two matrices are similar matrices. And similar matrices have the same traces. So whatever we obtain does not depend on the choice of beta. And this tells me that this chi is a well-defined function. Okay. The function that I define as chi is called a character of G, a character afforded by this representation X. So each representation gives me a character. I call this a character afforded by the representation that I started with. Okay. So look at this one. Whenever you have a representation like this homomorphism that we have from G to GLV, so it is a homomorphism. It means it sends the identity element to the identity element here. So chi X of 1, which I denoted by X index 1, this must be the identity linear operator on V. So it is from V to V. It sends any alpha to alpha itself. So if I choose a basis, as I told you, choice of basis is not important for us. So choose one arbitrary basis for your vector space and then fix it. I start working with this beta alpha 1 up to alpha n. Then what is the representing matrix of this X index 1 with respect to beta? So it fixes every element. Yeah. So it's an alpha 1 to alpha 1. So I have this column, the first column that we mentioned it here. Then it sends alpha 2 to alpha 2. So I have this column and continue like this. It sends alpha n to alpha n. So I have the last column. It means it gives me the identity matrix, which is obvious because the identity linear, the representing matrix of the identity linear transformation is the identity matrix. So according to the way that we define the character afforded by this representation, so character was a function from G to C, and chi of any element of G, any element that I choose in G, goes to trace of the representing matrix. So in particular, chi of 1, so it means trace of the representing matrix of X index 1 with respect to beta. Actually, this beta is inside the parentheses. So you have the identity matrix. Trace will be sum of these 1. How many times? It is just n times, which is exactly dimension of the vector space that you started working with. So what does it mean? It means if x is a character afforded by a representation, that was afforded by representation x, x was the representation, or actually the homomorphism from G to GL V. V was a vector space such that dimension of V as a vector space over C was n. So chi of 1 is exactly dimension of this vector space. So in particular, if you are working with vector spaces of dimension 1, so this chi of 1 is already 1, which is called a linear character. Okay, now here we will start working with irreducible characters and irreducible representations. But what do I mean by irreducible representation? Here I try to give the definition of irreducible representation according to the invariant subspaces, something with respect to linear algebra. So suppose you have a vector space like V and a subspace of this one, which is a proper subspace. This is called invariant under one linear operator of V. If W to the T, what do I mean by W to the T? It means image of T when you consider the image over vectors of W, it is again W. So what do I mean by irreducible representation? A representation is irreducible representation of G, like this homomorphism is called an irreducible representation of G if the vector space that I work with has no non-trivial invariant subspaces. So it means you cannot find except, okay, the zero space is, what is it? It is always invariant. And the vector space itself, V is also always invariant. So these are called trivial invariant subspaces. Except these two, you cannot find any other invariant subspace of V. So whenever I have an irreducible representation, then the character that I obtain out of this representation, the character afforded by an irreducible representation, is called an irreducible character. So this is what I explain here. An irreducible character is a character which is afforded by an irreducible representation. So if you are familiar with CG modules, so what do I mean by an irreducible character is a character afforded by a representation which is actually a representative or a homomorphism that we obtain from a linear action of G on a simple CG module. Yes. Okay, so this is a famous theorem in representation theory of finite groups that the number of irreducible characters of G is exactly the number of conjugacy classes of G. Distinct conjugacy classes and distinct irreducible characters, the numbers are equal. So if I know that G has exactly R distinct conjugacy classes, then I know that irreducible of G, this is a notation for the set of irreducible characters of G, has exactly R elements. So I denoted by chi1, chi2 up to chi-R. What do I mean by degrees of irreducible characters? I denote the set of degrees by CD of G. So it is exactly values of these chi-i's at a point 1. 1 was the identity of the group. Yeah, okay. So this 1 by this 1, I mean the identity of your group or 1G. And if you remember, each of these chi-i's, chi-i of 1, is exactly the dimension of the vector space that you work with. Remember, if chi was a character, then chi of 1 was dimension of the vector space V that we started with. As an example, so the first, I mean, when you want to discuss vector space, a finite dimensional vector space over the field of complex numbers, you may consider C itself as a vector space over itself. So it is a vector space of dimension 1. Now, when I have a finite group G, I can consider the trivial action of this group and this vector space. What do I mean by trivial action? By trivial action, I mean it sends any element of G, sends any alpha to alpha itself. So this is called a trivial action. Then, okay, out of this action, I can rewrite this homomorphism from G to GLV. Then you can see that according to the way that I define, you can see that chi index, X index G send any alpha to alpha itself. And here I'm working with a vector space of dimension 1. Yes. So any matrix that I obtain here is a 1 by 1 matrix. And according to the way that we define it here, so it will be actually the matrix 1. And this is true for any G that I choose in G. But what was chi? Chi of any G was the trace of such matrix. But any matrix for this representation is exactly a matrix, 1 by 1 matrix, which contains only 1. So its trace is only 1. So we have always 1 for any group that you think. You can always consider the trivial action of G on this vector space. And this one-dimensional vector space, C as a C vector space. So this action gives you a character such that this character sends any G to 1. So we know that, and since this is a vector space of dimension 1, so of course this is simple, yes. Simple CG module, or the representation that you obtain here is an irreducible representation. So the character that you obtain here is an irreducible character. But I know that the set of irreducible characters is, I denoted this by chi1 up to chi r. So we always, when I mention irreducible of, let me write it, when irreducible of G as chi1 up to chi r, by chi1 I always mean this guy. So it means for when I consider this irreducible character for any G that I choose in G, chi1 of G is always 1. Why? Because of the 1 by 1 matrix that I have here. Okay, now this was some actually basic results that we need to know. Now, what do I mean by a character graph of a finite group? Start with a non-empty set like X, but it is a set of positive integers. Okay, and it is a finite set. So what do I mean by rho of X? Rho of X is the set of all prime divisors of elements of X. So it means the set of all prime P, such that P divides N for some N in X. As an example, you may consider, for example, X equals 1 for 12. Yeah. So what do I mean by rho of X here? I don't have any prime divisor of 1 yet, so forget 1. Whenever you have 1 in your set, forget it. Now, the prime divisor of this one is 2. Prime divisors of this one is 2 and 3. So I have already 2 here, just I need to write 3. So rho of X for this X will be exactly the set 2 and 3. Now, what do I mean by a character graph or a prime graph? In some papers, it's written as prime graph or a character degree graph. We denote this graph by delta of X, vertex set. So by V, I mean vertex set. And by E, I mean edge. set. Okay, so vertex set of delta x is exactly row x, the set of primes that we defined here. And H set is the set of, let's say, P and Q, such that there exists one element of X like N, such that PQ, the product PQ, divides N. Let's see some examples to understand this better. So I started working with this set. They said 1, 2 cube, 7, and 9. So first, let's write a row of X, because this row gives me the vertices of this graph. So prime divisor, forget 1, prime divisor of 8 is 2, prime divisor of 7 is 7, and prime divisor of 9 is 3. So vertices are this, as I mentioned in this. So you have 2, 3, and 7 as vertices. Now, according to the definition that I mentioned here, I can join, when I denote this notation, it means this is one edge. There is an edge between these two vertices. So there is an edge between P and Q if the product divides one N inside X. So can I sketch one edge between 2 and 3? So I should look at X. Is there any element which is divisible by 6? There is no. So there is no edge between 2 and 3. Is there any edge between 3 and 7? So I should look at this one. There is no element which is divisible by 21. So I cannot have an edge here. In a similar way, you can see that there is no edge between 2 and 7. So delta X in this case will be a disconnected graph. It is disconnected because, for example, there are two vertices which are not connected to each other. There is no edge or no path between these vertices, and it has exactly 3 connected components. Now, another example, I have y as 1, 6, and 12. So again, prime divisors of this one, 2 and 3. Prime divisors of this one, 2 and 3. I forget 1. So the set of all prime divisors will be 2 and 3, which is row of y, which is the vertex set. So my vertices are here, 2 and 3. Is there any edge between 2 and 3? I should look at this set. So is there any element of X which is divisible by 6? Yes. For example, 6, or for example, 12. This was this was one special example that each of these elements is divisible by a product of 2 and 3, but this is not a general case. Okay. Anyway, 1 is enough for me. For example, when I see this, okay, there is an edge between 2 and 3. So here I obtain delta y, which is a connected graph. Now, here I started working with a non-empty set of positive integers, which was a finite set at the same time. But I want to discuss this graph for a group, for a finite group. So I need a set of positive integers with respect to a group. Okay. So I have a group. I need a set of positive integers with respect to G. You may find different sets. And actually, if you search, you can see different papers on these topics. So one consider the set of conjugacy class sizes. So the set of CS of G, this is the set of conjugacy class sizes. Here we will work with the set of character degrees. Remember the character degrees? This was the set of values of irreducible characters at the identity of the group. So instead of X, remember this definition, instead of X here, we work with X equals CDG. Okay? So given a finite group, G, what do I mean by delta of G? I mean delta of CD of G. Okay, so this delta G is just a notation for delta of CD of G, which is a set of positive integers, because these are dimensions of the vector spaces that you work with. Actually, the simple vector spaces that you work with. So simple CG modules that we work with actually. So these are, whatever I want to say is that these are positive integers. Yeah. So look at this example. I have a group which is a direct product of S3 and A4. So we have this property that if your group is a direct product, if for example G is direct product of H and K, then what can you say about CD of G is something like n times n, such that n is in the CD of H, m is inside CD of K. So if you know CD of S3 and if you know CD of A4, then you can see the product of these two. So it gives you 1, 2, 3, and the product of these 2 and 3, which is 6. So it will be exactly CD of G, which is a direct product of S3 and A4. Now, what is delta G for this group? So what are the primes? Okay, forget this one. Prime of this is 2, prime of this, prime divisor of this is 3, prime divisor of this is 2 and 3, so it is repeating, yes. So row of G here is exactly 2 and 3. I have 2 vertices, and there is an edge because I have one element which is divisible by the product of this. So delta of this group G, direct product of S3 and A4, is exactly the graph that we sketch here. Okay, so we have some results about actually some graph theoretical results for delta G while G is solvable, while G is non-solvable. But in my case, since I'm going to work with solvable groups, so I just wrote or mentioned those with respect to solvable groups. So G is a solvable group. Then n of delta G is less than or equal to 2. What do I mean by n of delta G? This is the number of connected components of delta G. So n of delta G, the number of connected components of delta G is at most 2. It means whether it is connected, while it is disconnected for a solvable group G, we have exactly 2 connected components. And for the case that we have exactly 2 connected components, it means we have a group whose delta G is disconnected, a solvable group. Then this group is classified into 6 types. Okay, if you check the paper of Lewis in 2001, then you can see this classification. And for the case that delta G is a connected graph, it means you have only 1 component, then diameter of delta G is at most 3. And we have some examples for the case that diameter is exactly 3. So this is best upper bound. Okay. Let me also mention something else. This Palpate theorem is also called as 3 primes conditions. What does it mean? It means that, let me explain here. It means that, okay, when I'm working with a solvable group, the solvable group, like P, Q, R, if you choose 3 primes in your vertex set, so P, Q, and R in row of G, then at least 2 of these vertices are joined by an H. So inside delta G for a solvable group G, you cannot find 3 vertices which are not connected to each other. So at least one of them. So there exists, for example, so without loss of generality, there exists, let's say, an H between, let's say, P and Q. So you cannot have 3 points like this. At least one of them is connected. Or if this is not the case, then these are connected. If this is not the case, then these two are connected. This is actually the Palpate Theorem, and this tells me that we have at most two connected components. As I told you, sometimes it is called as the 3' conditions. Okay. Now, look at this one. By these 3' conditions, we can see that if I'm given such a graph, and I want to see whether there exists a solvable group whose delta G is this graph, I can say no, there is no. Why? Because look at this P1, look at P3, and look at P5. These are 3 distinct vertices, and none of them is connected to each other by an edge. Okay, so there is no edge between these two, there is no edge between these two, there is no edge between these two. So this contradicts Palpate's theorem, or this contradicts 3' conditions. So such a graph is not delta G for any solvable group G. Okay, but for example, this was a path of length 4. Yes, this was P4, a path of length 4. But this is a path of length 1. P1 I denoted by this, path of length 1. This was a graph of a solvable group because direct product of S3 and A4, this is a solvable group. And as we discussed, delta G is exactly this graph, P1. What do I mean by a cut vertex in a graph, in any graph? It is a vertex whose deletion increases the number of connected components. As an example, look at this one. If you look at this graph, do I have any cut vertex? So first of all, I have one connected component. I have two vertices. One of them is, let's call this as A and B. If I delete it, I have only one point B. Again, I have one component. If I delete B, I have only one point A. So again, I have one component. So the number of connected components will not change. So I don't have any cut vertex here. But when you look at this graph, this one, for example, look at P3. If I delete P3, then I obtain this new graph. So if I delete P3, what do I obtain is this. P1, P2, P4, and P5. So I will obtain two connected components. It means P3 is a cut vertex for this graph, or P2 is a cut vertex, or P4 is a cut vertex. Okay, what do I mean by a block? A block is a connected graph without a cut vertex. Okay, a connected graph without a cut vertex is a block. So this is a connected graph, this one. It is a connected graph without a cut vertex, so this is a block. But this one is a connected graph without, but with a cut vertex, so it is not a block. Now, Zhang proved that you cannot find any solvable group G whose delta G is a path of length 3, which is denoted by P3. A path of length 3 is something like this. So here you cannot apply 3' condition because, for example, if I choose this prime, then, okay, forget this. If I choose this one, then these two are connected, or any other choices of these 3'. So here you cannot apply the 3' conditions, but you can see that, this is the result of Zhang, that you cannot have a solvable group whose delta G is a path of length 3, and this is something that they will use it. Also, Lewis in 2004, he proved that you can find a solvable group whose delta G has this structure. So it is a graph with diameter. Look at this one, 1, 2, 3. So diameter is diameter of let's say not delta G, because this is not delta G. Let's call this as gamma. The diameter of gamma is 3, and we have one triangle, so it has a unique triangle. It is a graph with diameter 3. So this graph is not the graph of the prime graph of any solvable group. Okay, now our main results. In order to discuss the result that I want to discuss, I need some notations. So start working with a finite solvable group. So finite solvable group, and delta G is a connected graph. Okay, and its diameter is 3. So when diameter is 3, look at this graph. Diameter is 3, I can find vertices, for example, let's call this as P1, let's call this as P4. Yeah. So you can find some vertices like P1 and P4 such that the distance is exactly 3. Because if you cannot find such vertices, then diameter is less than 3. Yeah? So definitely you can find one P1 and P4 in row G, such that distance between P1 and P4 is 3. So with respect to these 2 points, I define these 3 sets. Row 4 will be the set of those vertices such that distance with P1 is 3. Row 3, those vertices with distance 2 from P1. Row 2, those vertices which are neighbors of P1, neighbors, I mean distance 1, there's an edge. And at the same time, this point is a neighbor of some point in row 3, some point here. And at the end, by row 1, I mean the point P1 together with those neighbors of P1 which are not neighbors of any point here. So let's look at this graph again. So this is P1. Let's call it. Okay, this was also P4. Row 3. What was row 3? This was the set of vertices which have distance 3 plus from P1. So you can write this, if I call this as P5, this is exactly P4 and P5. This was row 4. Yes, sorry, I write row 3. This is row 4. Row 3, distance 2. So distance 2 will be only this one. Let's call this as R. Then row 2 will be those vertices which are neighbors of P1. So this is the only neighbor of P1, and they are at the same time neighbor of one element of row 3. So this is, let's call this as Q. So this is only Q. And row 1 here will be P1. So as you can see, union of row 1, row 2, row 3, row 4 will be exactly the set of whole vertices, which is row of G. And there's no intersection between these sets. So I obtain a partition for the set of vertices of delta G in this way. Now, this is a result us in 16. I forget how to read it. It says that the cardinality of union of row 1 and row 2 must be less than or equal to the cardinality of the union of row 3 and row 4. And in particular, this is very important, cardinality of row 3 must be at least 3 if we are working with a solvable group, if we are working with the prime graph or character graph of a solvable group. So actually, this is another way to show that this graph is not the prime graph of a solvable group whose diameter is 3. Why? Because look at row 3, it has only one element. But this tells me that we should have at least 3 elements if we are working with the prime graph of a solvable group. Okay, so the theorem that we have is that if G is a solvable group whose character graph is connected and delta G has at most one, then delta G has at most one cut vertex. What does it mean? Whether your graph has no cut vertex. Remember the case of S3 direct product A4 graph was this one. It has no cut vertex. or it has exactly one cut vertex. So because of this, we say that we have the character graph has at most one cut vertex. And in particular, if V is the unique cut vertex, it means if you are working with a case that you have a cut vertex and diameter is 3, then you have one of the following cases for your delta G. So whether delta G is like W, V, and Ks, what is Ks? A complete graph on S vertices, such that vertices of this complete part together with V, which is the cut vertex, does not generate a clique. Why? Because I want to have diameter 3. Because of this, they shouldn't generate a clique, a complete. What do I mean by a clique? I mean a complete graph inside your graph. Or you will obtain delta G in this form. It means you start with a complete part, you will end with a complete part, and in the middle you have a cut vertex V. But you have some conditions that M must be at least 8, S must be at least 2. Vertices of Ks union V, they should generate a clique, but vertices of Km union V, they shouldn't generate a clique. And in any case, degree of your cut vertex must be at least 4. So I think I have time, so I can discuss some parts. Suppose you have the cut vertex V. If you don't have a cut vertex, okay, then we are done. Suppose you have a cut vertex, we want to say that we have exactly one cut vertex. So because deletion of these cut vertex gives you actually increases the number of connected components, so it means that it shouldn't be an endpoint. So its degree must be at least 2. And so I can say that I can find something like this inside the graph delta G. Okay. Now, whether vertex is the vertex of degree 2 or because this is just a part of delta. If you're working with a case that degree of your vertex V, which is the cut vertex, is 2, then actually one of these R, you can see that the case that R is connected to some other vertices and also S is connected to some other vertices is not possible. So either R or S must be an endpoint. So without loss of generality, I can suppose that R is an endpoint of delta G. So what do I have? I will obtain a graph of this one. So R is an endpoint, V is the cut vertex. I have another vertex S, but this S, remember, this S is connected to some other vertices. I denoted by this red circle or disk, let's call it. What does it mean? This is KL. Why? Because of by 3' conditions, I can see that any vertex two vertices that I choose here, they must be connected. Why? Because, for example, if I choose a pair like 2 vertices of this one and then consider it together with R, by Palpate theorem or 3' condition, conclude that these two must be connected. What did I do? Okay, I can conclude that these two must be connected. So anyway, this is true for any 2 vertices here, and this means that KL generates a clique here. Not only KL is a clique, but vertices of KL and S together, they generate a clique. It means S is connected to any vertex of KL. Delta G will be something like this. But what can I say for L? Or do I have any upper bound for L? If L is 0, so you don't have this part. So what do you have? You have exactly RVS, which is a path of length 2. So you have only V as if you have a path of length 2. So you have RVS. This is obviously the unique cut vertex that you have, and we are done. If L is 1, then what do you obtain? So you will obtain a path of length 3. As we discussed, a path of length 3 is not the character graph of any solvable group, so this is not possible. If L equals 2, you will obtain this graph. As we discussed, this is not a graph of a solvable group. because remember, we discussed row 1, row 2, row 3, and row 4, and cardinality of row 3 was 1, which was not possible. So L is at least 3. We have at least 3 vertices here. And altogether, this tells me that cardinality of row of G is at least 6. So we are working with a graph whose diameter is 3. It's, I mean, in the case that we are working with diameter 3 and row at least 6 by a result of SAS, then you can check that, okay, this row 1, row 2, row 3, and row 4 will be something like this, but this contradicts the result of SAS. Actually, I mean this contradicts the result of SAS, because this row 3 must be at least a set with 3 elements, but we have only 1 element here, so it is a contradiction. What does it mean? The case that L is non-zero, or L is non-zero is not possible. So L must be 0. L 0, we obtain this part, a path of lines 2. And actually, it tells me that we have a unique cut vertex here, as we wanted to. This was for the case that degree of V is 2. What about degree V greater than 2? Then you can consider 2 different cases, whether delta G minus V has 3 connected components or delta G minus V has 2 connected components. The first case is not the case which is possible because of the 3' conditions. So it contradicts Palpate's theorem. So we have, when you delete V, the remaining part will be a graph with 2 connected components. So you will have 2 parts like C1 and C2, with vertices C1 and C2. And
Hocam,
then, yes.
Hocam özür dileyerek son 10 dakikamız kaldı. Hatırlatmak istedim.
Yes,
Teşekkür
I
ederim.
know. Okay, so you may consider whether you have a vertex in C1 with neighbors of V. So by n of V, I mean those, let's say, T in row G, such that, let's say, T and V is inside H set of delta G. So those vertices which are neighbors of V. So whether the intersection is 1 and or the intersection of C2 with neighbors of V is 1, or each of them has at least 2 elements in their intersection. So considering each of these cases, you can see that we have exactly 1 cut vertex. And in particular, if we are working with a case that diameter is 3, we can see that we have these 2 structures for delta G, as I mentioned. So whether you have a cut vertex in the middle, and then you have 2 complete graphs with these properties. V together with vertices of Km does not generate a clique, but V together with vertices of Km does not generate a clique, or you have this structure for your delta G. Now, this was somehow, okay, of course we use some group theoretical properties there, but we didn't see something like group theory here. So consider the case that you have a solvable group. Again, character degree is connected, and it has order n. It means we have n vertices, and we have a cut vertex V. Okay, and suppose that the CLO subgroup with respect to this cut vertex is non-abelian. If your group is K4 free, K4 is a complete graph with 4 vertices. It means you don't have anything like K4 inside your graph, and G contains a normal V complement, then this n, the number of vertices, must be at most 4. And delta G is either P2 or this graph. Okay, now, why do I have such a property? Because when I have a normal V complement, so I can write G as a semi-direct product of H and V. V is the CLO of G, which was non-abelian. This was non-abelian, yes. And H was the normal V complement. So by using the properties that we have in character theory, you can see that rho of H is exactly row of G minus V. So every prime that appears here except V is a prime in row of H. And you can see that any character that we choose in irreducible of G, whether V divides this character, the degree of this character, if not, then you can obtain a character out of this according to Galar's theorem, which is divisible by V. So what does it mean? V is a complete vertex in our graph. What do I mean by complete vertex? It is connected to every other vertices of your graph. So at the same time, this was a cut vertex. So when I consider these results, these row H equals row G minus V, V is a cut vertex, and V is connected to every other vertices of delta G, I conclude that delta H is a disconnected graph, and it has two connected components because we are working with solvable case. But the property that delta G is K for free tells me that each connected component of delta H has at most two vertices, and altogether I obtain the case n equals n less than or equal to 5. But for the case that n equals 5, I obtain this. This is a famous result that such a graph, K2 union K2, is not a graph of a solvable group. So n is less than or equal to 4, which is our case. I prefer to stop here, and just I will show you the references that we have. Thanks for attending and being patient. I'm done.
Chat'te ve YouTube'da herhangi bir sorumuz olmadı. Buradan sormak isteyen birileri varsa eğer.
Tamam.
Hocamızın bu notlarına erişebiliyor muyuz acaba?
Of course you can. You'll send me.
Okay then.
Başka soru yok sanırım. Hocam davetimizi kırmadığınız için çok teşekkür ederiz.
Ben teşekkür ederim davetiniz için.
Bir sonraki konuşmamız 16.40'da başlayacak. Görüşmek üzere.
Okay, I can stop.